Let's move to numerical solutions. There is some drilling going on with the construction outside my window. I've closed the windows, but I will see how bad the noise is in the recording. So let's look at some direct numerical solutions and iterative methods for Poisson's equation, which for steady state we wrote as del squared c equals rho as a function of x, and typically we are solving it on a grid like this. Could be spherical, could be global in extent, and so on and so forth, but this is the most typical way to get introduced to the methods, and the direct method, as we will see, is not very efficient. So there are iterative methods, but we have to go through these just to make sure we understand the principles. So here is our domain x direction. So here x direction is indicated by j, and the y direction is indicated by I. It doesn't matter. I and j typically are used for x and y respectively. And the diamonds here correspond to the boundary values, and the interior values are shown by circles when we discretize. So this is a grid with inner points and boundary points. Starting again with our Poisson's equation, del squared c plus del squared c del x squared plus del squared c del y squared equal to rho xy. We have discretization of the equation. Just for simplicity, we will just do it as the easiest second order estimate. So Cij plus 1 minus 2 Cij. So at Cij, the second derivative is written with points around. So in the x direction you have j plus 1 and j minus 1, and for the y derivative you have the other direction I plus 1 and I minus 1. So we are ignoring the higher order terms and assuming again for simplicity delta x equal to delta y and neglecting terms of higher order. This equation just becomes Ci plus 1j plus Ci minus 1j plus Cij plus 1 plus Cij minus 1 minus 4Cij equal to delta x squared rho ij. So the relation between the value we are seeking to its neighboring values and the source sink kind of term is shown here. There are many reasons in the real world where delta x need not be equal to delta y, and it's almost never is. If you imagine a sphere, which is what climate modeling is going to be on, then there are processes near the equator, for example, which need to be resolved better, where delta y will be very different than delta x, or in our case you can also think of mountains, latitudinal change in the domain, and so on and so forth. But without worrying about that, we can we can number the values instead of 1 1 1 1 let's see 1 1 1 2 1 3 and 1 1 2 1 2 3 and 2 1 3 1 and so on. We can just name them sequentially as 1 2 3 4 in some fashion, and unfortunately that number doesn't have to be unique, so you can go in this direction as 1 2 3 4 5 or you can go in this direction. And why does it matter? Because when you write it this way, we are writing, let's say, matrix of 1 1 1 2 1 3 2 1 3 1 and so on. That becomes equivalent to C1 C2 C3 C4 C5 C6 C7 C8 C9, or you can go also this way, C1 C2 C3 C4 C5 C6 and so on. So there is no unique way to do it, but it does have a consequence for the direct solution, providing you a matrix of this form, which again depends on the way the numbering is done. Here the vector r contains the values del x squared rho ij, so the source term at I and j, plus possible boundary values when you start at reach the boundaries or start at the boundaries. This is called a blocked matrix. You can see that there is a block here, block, so The matrix can be written in a block structure. The inversions, multiplications, everything get simplified when you have a blocked structure. But it turns out that the inversion is still dependent on which way the numbering is done, and pretty quickly you can see even for a 50 by 50 grid you will have 2500 elements of a matrix, so that's going to become very hairy very quickly. So there's another way to do it to avoid this kind of matrix inversion. They are called iterative methods. So we'll start with methods of relaxation and go into what are called methods of over relaxation. So successive over relaxation. So in this case we look for a stationary solution by going back to our original time dependent equation, where again k is assumed to be constant. So you have 1 over k dc dt is del squared c del x squared plus del squared c del y squared minus rho equal is the equation. So we look to solve for a steady state where dc dt goes to 0, which then allows us to write the discretization as Cij n plus 1. So the next time step is dependent on the previous time step plus discretization of the Euler forward. So it's Cij n plus 1 minus Cij n divided by delta t is the estimate for time derivative. Taking this on this side and rearranging the equation, you get k delta t delta x squared times ci plus 1j cn I minus 1j and so on, minus k delta t rho ij. Okay, so what does this give us? Basically, if we keep solving for n plus 1 and keep iterating till n plus 1, Cij n plus 1 minus Cij n goes to 0. So that's the iterative methods to find the steady state. So we have avoided the matrix inversion, but we have to now go through iterations. So here again CFL condition has to be valid, so k delta t or delta x squared has to be less than equal to 1/4 to make sure we have numerical stability. So if we just write the simple formulation that we looked at, Cij n plus 1 just depends explicitly on the known values and you keep iterating for equilibrium. This is called the Jacobi method, which actually converges very slowly. You have to keep on iterating for values to converge at each grid points. But there is a slightly modified method, the Gauss-Seidel method, which uses the values that are already known. So Cij n plus 1 is written now in terms of Ci plus 1j n plus Ci minus 1j n plus 1 plus Cij plus 1 n and Cij minus 1 n plus 1. So in each iteration you have found some values, so we can use those values and accelerate the conversion, convergence, quicker than the Jacobi method, but it is still not very efficient. Okay, so even the Gauss-Seidel method is not very efficient. In order to reduce the error of the solution by p orders of magnitude, i.e. by a factor of 10 to the p, about 1/2 p j squared iterations are required, where j is the number of grid points. So you can see that the number of iterations is going to go very quickly to a large number as the domain size becomes bigger. So how to improve on these? We have methods called successive over relaxation that we will look at in the next podcast. Again, these are brief introductions, so we take simple equations like the Poisson equation and provide introductions to the methods. Either you are just taking this for introduction to climate modeling, in which case you don't need to worry about the details beyond these. There are many details involved, as always, especially when you try to solve the actual climate model equations. But if you are getting into modeling, then you have to get into those details anyways. But this is a good starting point in terms of an introduction to the equations, numerical methods, and the various issues that are involved, and various approaches in which accuracy, speed of computation, and computing time or computing scales are optimized. Okay.